A very good afternoon, students. Very good afternoon to one and all. Good afternoon, Nikita, Sabrina, and Samira. So, am I audible? Can you able to hear my voice and can you able to see my screen? Just let me know in the chat box if you can able to hear and see the screen. Yes. Okay, fine. So, yeah, today I am unable to turn on my video due to some network issues. So, kindly adjust with me with that for today. Okay. So, if you have remember in the previous class, we have started with electrochemistry lesson, right? So do you guys remember? So we have completed the solutions lesson and we have started the electrochemistry lesson. And in electrochemistry, we have dealt with the electrochemical cells and some introductory part of that, and we have discussed about the Daniel cell, those things, etc. Okay. So today we are going to learn about the IUPAC representation of a cell, electrode potential, cell potential, Nernst equation, and applications of Nernst equation. So we'll try to cover as much as topic possible according to the availability of time. Okay. So now let's move on to the IUPAC representation of a galvanic cell first of all. So you can see the galvanic cell on the right side of your PPT, and at anode, what happens? Oxidation reaction occurs. I hope you'd be knowing this, no? So this is a galvanic cell in which we have two beakers. One beaker contains zinc sulfate solution and the other beaker contains a copper nitrate solution, and both are connected by a salt bridge, and the electrons are moving from the zinc to copper. Okay, from anode to cathode. So at anode, what happens? Oxidation occurs. Okay, means the oxidation half reaction occurs at anode. Okay, so who is getting oxidized here? So the electrons are moving from zinc electrode, right? Zinc. So means zinc is losing its two electrons. Zinc is losing its two electron and it is getting converted to, it is getting oxidized to zinc 2 plus. Okay. So the IUPAC notation for this particular reaction is this. So we have a line, a vertical line, which separates the zinc metal and the ion, zinc 2 plus ion. Okay. And at cathode, reduction happens. Reduction half reaction will occur. And the copper 2 plus ion is getting reduced to copper by gaining 2 electrons. Here is the reaction which we have already discussed. And the IUPAC notation for this is copper 2 plus, and you draw a parallel line, a vertical line, and then you put copper. Okay, copper inside the bracket we are putting small s, that denotes the electrode. Okay, now the overall cell reaction, oxidation half reaction plus reduction half reaction, which is called as the overall cell reaction, is represented using this reaction. Okay, and the IUPAC notation for the overall cell reaction has to be written like this. So how it has written? So first we have to write the oxidized part and then the reduced part. Means the reaction which is occurring at anode has to be written first. Then the reaction which is occurring at cathode has to be written. Then they should be separated by a parallel line. Okay, by a double line, double parallel line, you have to separate these two. So this is how we have to write the cell notation using IUPAC. Okay, clear. So do you have any doubts? Will you all be able to understand, or will you all able to draw a cell notation if I give you some other reaction, students? Do you have any doubts? Very easy. Just you need to go for the anode reaction and then go for the cathode reaction. That's it. So shall we proceed with the next topic? Just let me know in the chat box, students. If you can able to understand, just type yes. Or if you're having any doubts, just ask your doubts in the chat box. Give me a thumbs up. So give some response so that I can understand. And then move on to the next slide. Yeah. Thank you so much, Hacker. So next we will go with the electrode potential. Okay. So to understand the electrode potential, again I'm going to take a container, a beaker, and an electrode is dipped inside that, and we have an electrolytic solution, and that solution is called as zinc nitrate. Okay. Zinc nitrate contains zinc 2 plus and NO3 minus ion inside it, and also we have an electrode plate dipped inside that. Okay. We have an electrode plate dipped inside that, and we have the ions present inside that, and electrons are coming out from it. Okay. Now the potential difference developed between the electrode which is dipped inside the electrolyte. The potential difference developed between the electrode and the electrolyte. Electrolyte means electrolytic solution. Okay. So the potential difference developed between this electrode and the electrolyte is called as electrode potential. Got it? So it is also noted by electromotive force of that particular system. Okay. And for anode, with respect to anode, if the solution potential is less than the metal potential, okay, if the solution potential is less than the metal potential, then oxidation occurs. And in cathode, what is happening? Solution potential will be greater than the metal potential. Okay, so this electrode is a metal, and the electrolyte is the solution. If solution potential is greater than the metal potential, okay, so reduction occurs. So electromotive force, E reduction. Got it? Now, according to IUPAC convention, the standard reduction potentials are now called as standard electrode potentials. So, wherever you see this type of term, E0 cell or E cell, then you should be able to understand that it is nothing but the standard reduction potential. Nothing but the standard reduction potential. So, both electrode potential and reduction potential values are equal. Got it? So now next we are going to study about the standard hydrogen electrode, which is called as SHE. Okay. So when do we call the electrode a standard hydrogen electrode? It is called a standard hydrogen electrode if the condition is at STP. So what is meant by STP? Standard temperature and pressure. The standard temperature value is 298 Kelvin and standard pressure value is 1 bar pressure. Okay. Suppose I'm taking a solution. Okay. It is a 1 molar acidic solution, H plus solution. Okay. And I'm dipping a container system and I have some hydrogen gas. Okay. There is some outlet which evolves the hydrogen gas and the pressure of that hydrogen is 1 bar. Okay, which is a standard pressure condition. And the rod which I am using there is a platinum rod. Okay, and the rod which I am using inside that thing is a platinum rod. And I have some some metal block inside the system, no? So which is the platinum metal there. Okay, the platinum metal, and then the surface, this type of reaction is happening. Okay, so H plus is gaining the electron and it is getting converted to H2. So you see the reaction here, H plus, it is going and reacting with the electron and it is getting converted to H2. So the reaction is happening like this. And also H2 on the other side, what happens? You see here, H2 on the other side, losing its electron, losing 2 of its electron, it is getting converted to 2H plus. So I can write the reaction H2 giving 2 plus and 2 electrons. Now there is some potential value, electrode potential associated with this, right? So now it is represented by E naught of H2 bar, or I can say a vertical line with H plus. Okay, because H2 is getting converted to H plus. Now the E naught value associated with this is 0 volt. Electrode potential is 0 volt. And if I reverse this reaction, if hydrogen is gaining the electron and if it is getting if it is getting reduced to hydrogen gas, then again the E naught value associated with this is 0 volt. Got it? So if this is the case, then we can say that particular system as a standard hydrogen electrode. That electrode is called as standard hydrogen electrode. Okay. Now, the determination of standard electrode potential of metals. So, this is the next topic. Okay, under the electrode potential topic, these are some of the subtopics. So, to understand this, again, we are taking a beaker and an electrode dipped inside it, and it is a standard metal electrode. Okay, standard metal electrode, and which it is a metal rod, and the concentration of the metal ion is 1 molar. Okay, so here the concentration is given in terms of molarity. The concentration of the metal ion is 1 molar. Okay. And in the other beaker, we are taking this standard hydrogen electrode. Again, the concentration of that electrolytic solution is also 1 molar. Now I am connecting these two with a salt bridge. Okay. And there is some electrode potential, standard reduction potential associated with it. And it is denoted by E naught reduction. Got it? So this is how using this type of instrument will determine the standard electrode potential of a particular metal rod. Okay, if I use some other metal rod here, then I will get some other values. Okay, the metal can be anything. We can take any of the D block metals and we can take P block metal. The metal rod can be anything. So depending upon the nature of the metal and the type of the metal, so the values will change. E naught values will change. So now I have used this type of technique and I have got the E naught values for some of the metals, and I'm going to put all those values in a series called electrochemical series. Okay. So here you can see those values. So here you can see those values. So the elements are given in the first column, and the electrode reaction, in which in all the cases the electrons are gained, right? So it is a reduced form. So oxidized form plus gaining of electron leads to the reduced form of that particular element. And since it is getting reduced, the standard reduction potential values for this type of elements can be given. Okay, so we are getting these values from the previous slide setup which I have shown. Got it? And here if you see for hydrogen, the standard hydrogen electrode, the E naught value is 0. We have already discussed. And here you see below that, the E naught value is coming out to be positive, and above that, we have the negative value. So what does these values, positive values and negative values, indicate? If the E naught value is more positive, then the oxidizing nature of that element is more. Now here in this tabular column, the fluorine is having the more positive value. Means fluorine is a strong oxidizing agent. What is meant by oxidizing agent? The species which accepts the electron so easily. The species which can accept the electron so easily are called as oxidizing agents. Electron acceptors are called as oxidizing agents. Okay. And if we have the more negative E naught value, then it is called as a strong reducing agent. So among the given elements, lithium is the strong reducing agent. Lithium belongs to S block, and it will donate its electron so easily. So electron donors are called as reducing agent. Okay. So lithium is the most reducing agent, more strong reducing agent, and fluorine is the more strong oxidizing agent. So we are determining these values using the setup which we have discussed. Okay. So students, can you able to understand all the topics till electrochemical series which we have discussed so far? Do you have any doubts? Do any of you have any doubts from the electrode potential value and the electrochemical series? Yes or no? Ashwin, Divyanush, Nikita, Hacker, is everything okay and clear for you guys? Okay. So you don't have any doubts so far, right? Okay. So if you're having any doubts, you can put that in the chat box. I'm here to clear those doubts for you. Okay. So now let's move on to the next slide, which talks about the selection of oxidizing and reducing agents. So how to select an good oxidizing and good reducing agent. So to understand this, let's take two reactions. So here in these two reactions, in the first reaction, Ag plus is ion is gaining one electron and it is getting converted to Ag, and for Cr3 plus, 3 electrons are required to get converted to Cr, chromium metal. Okay. Now let's go for the E0 values for this. So from this given table, the E0 value for Ag plus 2 Ag is plus 0.80 volt, plus 0.80 volt. So if Ag plus is taking one electron, the value is plus 0.80. Yeah, Samira, which slide you want, my dear? Which slide? The previous slide, electrochemical series slide you want? Samira, which slide you want me to show? Second one means we have already come across many slides, no? Can you tell me the topic of that slide? Is this the slide you are asking? Electrochemical series slide? Is this the slide you are asking? Just let me know. Let me know quickly. Second one means before this electrochemical. Okay, wait. This one? This one you want? Okay. So, are you drawing this picture in your notebook or taking the screenshot? So I would recommend you to take the screenshot of this and later you can draw this in your notebook, okay? So because it will take some time now to complete everything. So take a screenshot of this and then, yeah, fine, good. So students like this, if you want me to show any slides, I'll show for sure, okay? So you have my ultimate point is you guys should understand the thing. Okay, without understanding, don't go for the next topic. So stop me whenever you want me to stop and ask your doubts. Fine. So somebody is trying to record the meeting, I think. So it is already recorded. I am recording here and I am uploading this in the YouTube also. Yeah. And within few days, the same thing will be telecasted in YouTube also at the same time. Okay, so there is an issue with the thing. So that will also be rectified soon. It is recorded and it is getting uploaded in the YouTube. Once I finish this class, you can get this in the YouTube. Is it okay? Is it fine for the person who was trying to record this? Yeah. So let us move on to the next thing. So we have completed the electrochemical series and we were discussing about the selection, right? Yeah. So now the E0 cell, E0 value, electrode potential or the standard reduction potential value associated for the first reaction is plus 0.80 volt. And for chromium 3 plus to chromium, if you see, it is minus 0.7. If the reduction potential is higher, then the tendency to get reduced is also higher, right? And it is a strong oxidizing agent. So among silver and chromium, Which one will undergo the reduction easily? Silver or chromium? Any idea? Higher the reduction potential, higher will be the tendency to get reduced, and better is the oxidizing agent. Okay. So silver is the one which will undergo reduction. So more positive means it is a strong oxidizing agent. So silver is the strong oxidizing agent compared to chromium. So oxidizing agent means it can go and gain the electron easily and more effectively compared to chromium. So if silver is having the ability to gain the electron more effectively, then the oxidation state of the silver is changing. No, from +1 to 0. So +1 to 0 means it is reduced. Silver is getting reduced. So it is undergoing reduction by acting as a strong oxidizing agent. So all oxidizing agents will get reduced and all reducing agents will get oxidized. Because oxidizing agents are electron acceptors and reducing agents are electron donors. So this point is very important. Higher the E naught value, higher will be the tendency to get reduced. Okay. And in the other way around, vice versa, lower the reduction potential, higher will be the tendency to get oxidized and better is the reducing agent. If the E naught value is very low, then that element can act as a strong reducing agent. So here chromium is having the more negative, more lower value, smaller value. So it will undergo oxidation. Okay. So oxidation means it will lose its electron than gaining the electron. Okay. So these 2 points are very, very important because in the questions, they will give you some 3 to 4 reactions like this, and they will give the E naught values also. And they will ask us to find out the strong oxidizing agent from the given 4 species. Okay. So how will you find out? It is very easy. Just by looking into the E naught values, you can get the answer. If it is more positive, strong oxidizing. If it is more negative, strong reducing. That's all. If they're asking you to find out the order, go with the more positive to negative. Okay. So very important, but easy. So don't get confused here. Is it clear for all of you? Will you be able to find out the strong oxidizing agent and strong reducing agents if E naught values are given to you in the question? Yes or no? The E naught values are more positive, then it is a strong oxidizing agent. And if the E naught value is more negative, then it is a strong reducing agent. That's all. So this is the concept which we are discussing in this slide and in the previous slide. Students, is this clear for all of you? Shall we go on to the next thing? Give me your answer quickly. First, one of you reply me soon. Do you have any doubts? So I have to call out your names or no? No, no. Nikita, can you able to understand? Hacker? Yes. Okay. Now next coming to the reactivity of metal. So I'm going to take the same 2 reactions with silver and chromium with their E naught values. Okay. Now we are going to see which metal is more reactive. So we have already studied that lower the reduction potential, that is more negative, higher will be the reactivity of metal. Higher will be the reactivity of, yeah, okay, Nikita. Fine. You have understood. Good. Fine. Lower the reduction potential, higher will be the reactivity of metal. So, chromium is the more reactive metal among these two. Okay. So the one which is acting as a strong reducing agent will be more reactive in nature. So that is the concept. So here the reduction potential E0 values are inversely proportional to reactivity. If the E0 values are very lesser, then the reactivity is more. Got it? So write this relation and keep this in your notebook. So now let's go with one question from the topics that we have discussed. I'm going to ask you one question. Can we store copper sulfate solution in silver vessel? Can we store copper sulfate solution in silver vessel? What is your answer? Is it yes or no? Can you able to store copper sulfate in silver vessel? First say yes or no, then we will go with the discussion. Like why it is yes or why it is no. We'll go with the reasons later. Now give me the answer with yes or no. No? Okay. Actually, the answer is yes. Okay. You can store copper sulfate solution in silver vessel. Okay, we'll discuss. Okay, Samira, we'll discuss now. So, we have already know that the copper E0 value for copper 2 plus 2 copper is plus 0.34. This I have took from the electrochemical series table and it will be given to you in the question, okay? So, you don't have to worry. And for Ag2 plus 2 Ag, it is plus 0.80. Lower the reduction potential, higher will be the reactivity of the metal. So, this is what we have discussed, right? So, now here silver is less reactive. So thus, silver cannot displace copper from its solution and no reaction will occur. Okay, silver is less reactive. So since silver is having the more positive E0 value, the reactivity of that silver will be very less. So it cannot react with the copper and it cannot displace the copper. So we can store this copper sulfate in a silver vessel. Okay, the silver will not react with this copper and it will not undergo any reaction. So is this clear now for all? So you are not given with the values in the question, no. So that's why you guys have had little difficulty in answering this question. I think by now everything is clear for all of you. Am I right? Do any of you have any doubts still? Shall I go with one more question, students? Shall we go with one more question? Shall we go with one more question? Is this question clear to all of you? Some a less reactive metal cannot displace a more reactive metal. So we can store the more reactive metal in a less reactive metal vessel without getting stuck. Okay. So I'll go with one more question for you. So given the standard electrode potential, arrange these metals in their increasing order of oxidizing power. So here we have four species values. Okay. So we have to arrange them in the increasing order of their oxidizing power. So we already know that higher the electrode potential, higher will be the oxidizing power. So I have given you two relations now in the previous slides. So in that we have studied this concept. So just check from the four values, which one is more oxidizing in nature. Can you tell me the name of the metal which is having the more oxidizing power? Is it copper or iron or chromium or zinc? Which metal is having the highest oxidizing power? Which is having the highest oxidizing power? Very good, Nikita. It is copper. Very good. After copper, The second most is, yeah, Samira, good. Second is iron. No, second is iron, then chromium, then at last only zinc comes because it is having the more negative value, right? So the order will be copper, iron, chromium, and zinc. Very easy, no? Just by looking into the values, you can find out the answer. Okay. So here, the IUPAC notation and the other things are getting over. The electrode potential topics are getting over. Now, next we will jump to cell potential. Okay. The next topic is cell potential. Just give me some. So, to understand the cell potential, again, I am taking a galvanic cell. So, in the galvanic cell at anode, what happens? At anode, what happens? Oxidation occurs at anode. Oxidation occurs at anode. Zinc will get oxidized by the removal of 2 electrons. And the E naught value associated with zinc is 0.76 volt. And at cathode, copper will be reduced and the E naught values associated with this copper is plus 0.34 volt. And the overall cell reaction is this. Here is the overall cell reaction. Okay, and this is the cell notation. Okay, this is the cell notation where the concentration of both the species is 1 molar and the E naught cell for this particular reaction has to be written like this. E naught of copper 2 plus to copper and E naught of zinc to zinc 2 plus. Okay. So cathode plus anode potential values. Okay. Now here in one thing oxidation is happening and in the other electrode reduction is happening. So oxidation E naught value will be the negative of the reduction E naught value. Right. Oxidation E naught value is the negative of reduction E naught value. So what I can do, so this is the oxidized part. This is zinc is getting oxidized to zinc 2. And if I am reversing this, then I have to change the sign from plus to minus. That's all. Okay. Which actually denotes E naught of cathode minus E naught of anode. E naught cell is equal to E naught of cathode minus E naught of anode. So this R denotes the reduction potential, okay, which is the very important formula for solving many numericals, okay, to find out the E naught cell, okay. Reduction potential value of cathode minus reduction potential value of anode. Just take a note of it. Very, very important. Okay. Now let's go with the next slide. So here I am taking that cell, okay, E naught value for both is written. And also we have studied this cathode minus anode formula. Now find out the E naught value. So what is the E naught value for cathode? Cathode reduction happens. So copper 2 plus is getting reduced to copper and the value is for plus 0.3. And at anode, oxidation occurs. But here I have reversed, no, reduction potential, right? So just you can substitute the values as such. So if you just add these two, you will get 1.10 volt for this setup, for this galvanic cell. So for a working of galvanic cell, E naught cell is positive. It is plus 1.1 volt. It is positive. See, in the April month, we have completed the solutions. Okay. So we have been given a schedule for you. Okay. So we are going in accordance with that. So we will complete this electrochemistry and we will start the chemical kinetics in this month. Okay. The full of electrochemistry and chemical kinetics will get over by this. Is it okay? Yeah. Now next coming to the feasibility of reaction. Feasibility of reaction. So to find out the feasibility, we need the delta G naught value, right? So delta G naught is equal to minus NF E naught cell. So this equation, this formula, I have already discussed with you in the previous class. in the first class of electrochemistry, where delta G is the Gibbs free energy of a cell reaction, and N denotes the number of moles of electrons exchanged, and F is the Faraday's constant, and whose value is 96,500 coulomb per mole, and E naught is the EMF, electromotive force of the cell. Faraday's constant value is constant, okay, and you have to memorize that value. If this E naught cell is greater than 0, then it denotes, or you will get delta G as negative or less than 0. Okay. If delta G naught value is negative or if it is less than 0, then the reaction is spontaneous. The reaction is spontaneous. In the other way, if E naught cell is less than 0, then G naught cell will be greater than 0. It will be positive. And the reaction is non-spontaneous. Reaction is non-spontaneous. Okay. So for a reaction to be spontaneous, the delta G value should be negative. So that is the concept for the entire physical chemistry. Okay. And if in the third case, if E naught cell is equal to 0, then delta G will also be equal to 0 because 0 into anything will be 0. So then we can say that it is in equilibrium. Reaction is in equilibrium. Okay. So these three results are getting from the given equation. Okay, so we'll solve one question for today's class session and then we will wrap it up. Got it? So we are asked to calculate the cell potential of following galvanic cell, and the E naught values for each couple is given. So, and three cell notations are given, representations are given. So let's go with the answer. So here are the values of each and every species, and we know the formula E naught cathode minus E naught anode. Okay, so taking the first reaction, so in cathode reduction happens. Okay, in cathode reduction occurs. So Ag plus is getting reduced to Ag here. So silver is the one which is getting reduced, and its value Ag plus Ag value is given as 0.80, and the oxidized zinc 2 plus values in terms of reduction potential, it is 0.76. So just substitute and add those things and get the answer as 1.56 volt. Okay. So in the same way, you can go with the second reaction also. So copper is getting reduced. So the copper value is plus 0.34, and for iron it is minus 0.4. Okay. So just addition will give you the answer. And the third reaction, third representation of a cell is silver and chromium couple, in which chromium is getting reduced and its value is minus 0.74 minus of gold value. It is 1.42. Add those two and get the value as minus 2.16 volt. Okay. So can you able to understand how to apply the formula which we have studied the numericals? Students, is this clear to all of you? So will you be able to answer if this kind of numericals are asked from the electrochemistry topic? Yes. Okay. Okay, my dear students. So today we have discussed about the IUPAC nomenclature, IUPAC representation of the cell, and then we have discussed about the electrode potential and then cell potential. And we have solved some numerical part. So in the next class, we can continue with this. Okay, we'll do some more problems and then we'll go with the Nernst equation. Okay. So try to join on time from tomorrow onwards. Don't be late. Okay. How to identify cathode and anode? See, cathode is the negatively charged electrode and the anode is the positively charged electrode. Okay. So by looking into the sign, you can find out. Otherwise, you can find it from the reaction also. The species which has undergone oxidation, so that reaction has happened in anode and the reduction have happened in cathode. You have got it? Okay. Okay, Kamal. From which JNB you have come from? May I know the name of your JNB? Fine, fine. Malapur. Okay, my dear. Okay, students, thank you so much for listening to today's lecture. See you all, meet you all in the next session. Thank you. Bye-bye.